ado, let's welcome Arjun.
Thanks for the introduction, and this thing is on, right? Great. So thank you all for coming, and thanks for having me here. As Joran said, I'm Arjun. I'm a professor of computer science at UMass Amherst out in Western Massachusetts. And yeah, this is sort of one of several projects that are going on in my lab, and it's a pretty typical example of the kind of thing that I like to do, which, as you said, is sort of bring programming languages and verification techniques to like messy systems problems that people generally thought were sort of immune to sort of clean solutions. And so today what I'm going to talk about is system configuration languages, Puppet specifically. Just from some of the conversations I was hearing, it sounds like there are people in the room who have worked with Puppet, Chef, Ansible, things of that sort. Could I get a sense if you raise your hands? Okay, awesome. You be patient at first, as I'm going to sort of introduce these system configuration languages for the general audience. Okay, so I want you to think about the problem of setting up a web server. Right, so let's imagine if you wanted to set up a web server. Okay, so the first thing you might do to do that is install your favorite web server. Maybe it's Apache. Now that doesn't do anything, right? All that does is sort of set up the default welcome to Apache web page. So you got to edit the Apache site configuration, point it to your actual web page. After that, you need to actually restart the web server because it doesn't pick up your configuration changes. And then when you go to your web browser, you probably made a mistake the first time. Maybe there's like a typo in your directory or something of that sort. All right, so you go back to your terminal, you edit that configuration again, restart it again, test, this time it works. Okay, so there's probably a couple of more things you need to do if you're serious about what you're doing. Maybe you want to block SSH access, not if you're using Ansible, that people I was talking to about this. Maybe you want to mount some sort of backup volume, use a cron job to set up some sort of backup. All right, now imagine that your website starts getting a lot of traffic and one web server is no longer enough, right? And so what you need to do is spin up 3 more web servers. Okay, I hope you all were taking notes because I can't remember those commands anymore. All right, so this is a problem. So in practice, if you have even a moderately sized organization, you probably have lots and lots of computers, not just 3. Some of which may be Mac machines, some of which may be Windows machines, some database servers, some web servers, and sort of configuring all of these computers is a problem. In fact, we all know that software bugs are a problem, but a lot of the major systems outages that we've been hearing about over the last couple of years have been not software bugs, but configuration bugs, both system configuration bugs and network configuration bugs. So for example, I think this was a year or 2 ago, the New York Stock Exchange went down for about, for a couple of hours, and it was, the root cause was determined to be a configuration error, not really a software bug, like a difference between testing and production environments. A different kind of configuration, so there was like a military plane crash that was attributed to incorrect settings in the ECU. Perhaps the worst of these was a Facebook outage. I think it was early last year. Facebook went down for 2.5 hours. Everybody panicked. People started calling the police. The police replied, not on Facebook because it was down, but on Twitter, telling people to go outside. So system configuration errors are problems that your average human notices. All right, and so that's where configuration management languages come in. All right. These are just a small sample of some of the configuration languages that are in use today. There's several more that you might have heard of. The ones along the top are, let me say, sort of contemporary languages. The ones along the bottom are somewhat older. So there's Nix, which is a lot of fun. Some people might have seen this as like this Haskell-based sort of immutable configuration language. I can talk about how that relates to these in more detail if people want. Oh, and by the way, feel free to just like interrupt me if you have any questions. I will deflect questions or tell you to shut up if I need to. Right? So just raise your hand or just start yelling. Okay, so what I'm going to talk about today is Puppet, all right? So it's why Puppet? So one reason is that it's very popular. There's like over 30,000 organizations that used Puppet the last time that they reported these numbers. Though a lot of the things that I'm talking about, that I will talk about, a lot of the techniques and tools that we've developed for Puppet should be possible to reproduce them for these other system configuration languages too. And so talk to me more about what I think. I'm not going to talk about that in great detail, but if you're interested, come talk to me and I'll tell you what I think the unique challenges are in domains like Chef and Ansible and whatnot. Okay, so a little bit about how Puppet works. So Puppet follows a sort of client-server architecture. So you have your Puppet master, which has configurations for your entire organization, and these configurations are pushed down to various machines. Right? That's all I want to talk about as far as the architecture goes. One other thing, the idea is that as you update your configuration on the master, the changes are automatically propagated down to the machines that have the Puppet agent running on them. Okay. What I want to focus on is the Puppet configuration language, right? And so let me sort of talk about that using a small example. So here's the smallest Puppet configuration file I could think of. All it does is create an authorized key file in my home directory, right? And in this particular one, this is not good Puppet. I have sort of an inline public key as the content of my authorized key. You don't have to do this, of course. You can also say source and have it load keys off some remote server. You can add some more attributes. So it turns out that if this is what you actually write down, by default, Puppet creates a file that's owned by root, which is probably not what's intended here. So you can also specify ownership and permissions and group like that. Now, one other thing, if the .ssh directory doesn't exist, creating this configuration will fail. You can create that directory separately, but the simplest thing to do is probably to say force arrow true, and what that does is create parents as necessary. Now, if the user already has something in there and you don't want to sort of blast it away, you might say backup. You may use the backup attribute to say backup the old version. If that's not what you want to do, you can also say like replace false to sort of not blast away users' changes in case you want to preserve changes that someone has made locally. If all of this is too complicated, there's a built-in resource called SSH authorized key that sort of abstracts management for that file. Right, so Puppet has many different kinds of resource types, as they're called, that do this kind of thing. All right, so hopefully get a sense of what's going on here, right? So think about all the sort of low-level operations that are involved in doing all this kind of stuff, right? So what Puppet is giving you is, let's call it a declarative specification of machine state, right? So what makes a language declarative? So what makes a language declarative? Does anyone have any definitions or guesses on that? Yeah?
So the way I like to think about it is that it tells you what it should do as opposed to how.
Right. Yeah, that's exactly what Puppet says, right? So the Puppet Lab says it tells you what as opposed to how to set up the machine, right? That's a pretty solid definition. Any others that people can think of? So is OCaml declarative? Yeah.
I'm just going to say it's idempotent, so.
Yeah, okay, we're getting to, okay, great. Anything else? Okay, but that's a good one. We'll get to that. Yeah?
I often feel like declarative is just a code for easy to reason about.
Yeah, easy to reason about. Okay, so, I mean, you're all right. So I think when you say declarative, what you really mean is that there's certain kinds of properties of the programs in the language that you can reason about. So, for example, and I'll get to idempotence in a sec, so one of the properties that you might care about in system configurations is that they be deterministic, right? So, declarative is not a replacement for testing. You still got to test things, right? So, for example, maybe you write a manifest and you test it out in some sort of virtual machine, and everything works fine. You might want to know that when you actually deploy that manifest in production, I'm going to try to like avoid Puppet jargon. So manifest is Puppet jargon for configuration. So when you deploy a Puppet manifest in production, you might want to know that those systems are sort of set up in exactly the same way as in testing, right? So the other property that's much touted about Puppet is that it's idempotent. Essentially, what happens to sort of oversimplify things a little bit is that the system is the configuration is sort of repeatedly applied to the system to ensure that the system is in sync with the specified configuration. And so what that means is that applying the same configuration twice should do nothing, right? So manifest ought to be idempotent. All right? So let's just start with these two basic properties to begin with. Manifest should be deterministic and manifest should be idempotent. Just to be clear, these aren't properties that I'm making up. If you go to the Puppet documentation, you'll see that they say that feature of the system, first one, idempotency. And there's a sort of desire that, system configuration should be deterministic. All right. So given that these are desired features of the language, is it really deterministic and idempotent? All right, let's start with that. You're shaking your head. All right. So okay. You can go online, and there's all sorts of blogs that talk about like how to write good Puppet code. So I'm not going to do that. I'm going to give you some examples of small examples of terrible code. And just bear with me for a moment, just for a couple of slides. We're going to look at some terrible system configurations. Okay. So. Here's a really small example of a Puppet manifest. All right, so there's 3 different resources. Create a user account, we create a file called vimrc, and we install the vim package. Okay, everything seems fine, but there's this thing about Puppet. If you don't explicitly specify the order in which resources are installed, it's free to install resources in an arbitrary order. With some small caveats. So what may happen here is it may actually try to create the file before the user account. It actually does in this example. And so unless you sort of write down that edge, that's what happens here. It'll error out unless you write down that edge. Okay? So let's think about why that might be the case. So this seems totally obvious. It seems like, user account, file in the user's home directory, it should figure out that edge should exist, right? Can anyone think why it can't infer that edge needs to always exist? So, imagine you're not using, Linux, and you're using like Mac OS or, heaven forbid, Windows, right? You can't assume that the home directory structure is different on different operating systems, which is why that edge is not automatically created. Okay, so so what's interesting here is that Puppet tries to sort of be consistent. It doesn't when there's sort of choices to be made, it doesn't sort of randomly pick different orders. So it picks different sort of lexicographic orders. So it's the case that if you rename Carol to Alice, it works correctly, but with Carol, based on whatever ordering it picks, it doesn't work. Okay. So here's another example. Okay, so here's something that you might want to do. You might want to install Go because you like Go, and you might want to remove Perl because Perl is terrible, right? Seems like a pretty reasonable thing to want to do. Okay, so unfortunately, under Ubuntu Trusty, this is not true anymore, but under Ubuntu Trusty, it turns out that the Go compiler depends on Perl. I don't know why. It's not relevant. It just does. And so think about what this does, right? So if it, and the other thing is that Puppet doesn't sort of read package level dependencies. So it's up to you to sort of specify dependencies if necessary. So if it sort of executes this one first, it's going to first remove Perl and Go if it's installed. And then when it runs that one, it's going to install Go and Perl. And if you run it again in the other order, it's going to first install Go and Perl, and then once it runs that, it'll remove Perl and Go. Okay, so this is like a manifest that may have a system flip back and forth between 2 different states. Okay, so there's an easy fix to all this, of course. We can simply pick an installation order. Right. So, for example, let's just consider a little bit of a straw man solution. Let's just take all the resources and fix an installation order. So, for example, we'll just pick that one. If you pick the wrong one, we'll at least get a deterministic error and we can fix it. Out here, well, I would argue that picking an installation order isn't the right thing to do. It's that neither order makes any sense, but let's just entertain that solution for the moment. So you can do this if you want, but the problem with sort of having a fixed installation order is that it tends to break modularity. All right, so let me introduce one more Puppet feature, which is that Puppet lets you sort of organize your configuration into independent modules. All right, so here we have a module called CPP, which installs, make M4 and GCC because, that's what's involved in building lots of C programs. And here we have another module called for setting up an OCaml developer's toolchain. It includes the OCaml compiler and make an M4 because a lot of packages use make an M4. All right, so, and then we can instantiate both modules in case I want to set up a box that has both C++ and OCaml developer tools. All right, so the problem is that if these two modules are authored by two different people and they sort of fix different orders between M4 and make, you wind up with a cycle in the dependency graph, and the two modules aren't co-installable. Right? So it's actually important that these manifests be sort of loosely constrained so that co-installability is possible. Okay, so any questions so far? Okay, so I want to give just one last example of Puppet. This is sort of contrived, but here's a manifest that's not idempotent. All right, so this says we got to run that one before that one. So this one creates a file, and it basically copies file 2 over to file 1, and then we say file 2 must be deleted. So you run it once, it works. You run it the second time, that one blows up because the second operation deleted file 2. Right? So that's a trivial manifest that's not idempotent. Okay. So, stepping back, so what we're after is sort of showing that Puppet manifests are truly deterministic and idempotent. Right? And so let's think about, I want to think about, well, before we think about how we're going to actually establish that, let's think about the various things that make this hard to establish. Right? So one of the issues in Puppet is that there are many, I think over 50 different built-in resource types. This is a slightly outdated list. And there's many more different, many more sort of custom resource types that people have written using like Puppets like Ruby, Ruby-based sort of plugin framework. So all of these resource types, I mean, fundamentally, since we're installing software, they fundamentally set things up in the file system, and so there's sort of this endless, there's possibilities for endless interactions between them, right? And it's the interactions where these properties are violated. So apart from the sort of vast number of resource types that Puppet has, Puppet is also actually a pretty complicated language. So this is it's kind of small. It's like a list of features. This is the kind of, it's one of those tables where people sort of brag about how great their language are by sort of enumerating the number of features it has, which I have strong opinions about. So as you can see, they've kept sort of adding features as versions have gone on. They've also like removed features, which is sort of troubling when you're a programming language. One thing I'm happy about is that Puppet hasn't had dynamic scope since 2012. So if people don't know what dynamic scope is, we don't have to deal with that. But Puppet still has a lot of like crazy linguistic features, many of which aren't found in your conventional programming language. Okay, so I'm not going to get into all of this in great detail. It's frankly, a lot of it is pretty boring. The interesting thing here is that a lot of these crazy features of Puppet can be modeled as data log rules. And you can effectively take a Puppet program and have it generate and from it generate a data log program, which, when evaluated, the generated tables encode a graph between primitive resources. All right. So this is sort of the first step in our toolchain, right? We go from Puppet with all its sort of crazy complexities via data log to just a graph of like atomic resources with attributes. And what that lets us do is think about properties not of Puppet, but of resource graphs. All right, so when I say, so let me briefly talk about like other system configuration languages. everything I talk about from here on will really be about reasoning about about resource graphs and not Puppet. So if you wanted to sort of port these ideas to something else, like Chef or Ansible, it's about building a different front end here. Okay, so I want to first start talking about showing that Puppet configurations, really resource graphs, are deterministic. Okay, so quick straw man. I want to point out that testing is intractable, right? So one thing you can imagine doing is taking a Puppet manifest and trying to install resources in all possible orders and verifying that they all sort of produce the same result. But you very quickly get into like a sort of state space explosion problem, right? So you can't really do that. So that leaves static analysis. Yeah, okay, so the problem with static analysis, yeah, go ahead.
I think a stronger argument is for, yeah, complete graph, you have a lot of values for each node of the graph. Is that what you're basically saying?
I'm sorry, could you repeat the question?
Are you positing that basically you can practice like for each configuration value has many values and it has many relationships with many other configuration values, and that's why it explodes?
I'm saying that in a well-structured Puppet manifest, there's a potentially exponential number of possible orders in which things may be installed, right? Given a fixed manifest, Puppet will always pick one, but once that manifest is composed with others, other installation orders get exposed. And exploring that exponential space is intractable. We've also tried it with Docker containers and things of that sort. It takes a long time, even for pretty trivial manifests. Is that clear? Okay. Yeah.
You mean it's impractical in the sense that it's impractical to spin up machines, try them out for real, as opposed to?
Yeah, I mean, you would need it's just an exponential search space.
Okay.
Okay, so that leaves static analysis. The problem with doing static analysis is that all these resources sort of mutate machine state. And again, remember, there's 50 different resources and there's endless possible interactions. Okay, so the next step in our toolchain, we go from graphs of resources where a resource is like a labeled node with several attributes for a file, the path, the contents, etc., to a graph of little file system manipulating programs. Right? And so what these programs are little imperative programs written in a toy. Think of it as it's basically like the while language for people who've seen this in program analysis textbooks. Small imperative programs with built-in primitives that let you modify systems, that let you model updates and tests on system state. So instead of getting into that language in detail, I'm just going to show you a little example. This is somewhat simplified from what our system actually does. Okay, so for example, let's say we had that resource. So we're going to create the authorized keys file, and its content is that. So that turns into that program. And so some of the details of Puppet are sort of becoming clearer here. So what this does is check to see whether that's a file. If it is, it removes it and then creates it, right? That's what that program does. On the other hand, if you add the replace false attribute, we get that program. So if the file doesn't exist, we create it, but if the file already exists, we sort of leave it in place. And then if you say force arrow true to create the directory tree, we get this much longer program that sort of sets up the directory tree. Yeah?
So the thing on the left is a Puppet program.
Yeah, this is
the right is also a Puppet program?
No, the thing on the left is a Puppet program. The thing on the right is our modeling language, which is this imperative program with low-level file system operations like make, dir, is, dir.
Like a language you're using for kind of explaining what the thing is.
Yeah, this is a language that we made up. That's the simple language on which we're going to do our analysis because it makes the sort of interactions between Puppet resources manifest.
And the real implementation language of the resource on the left-hand side is Ruby.
Is Ruby, yeah.
And are you going to analyze the Ruby itself?
No, we're not going to do that. I'm going to talk about, I'm going to get into things of that sort later. But for the moment, what we're doing is we're modeling the semantics of the resources using this language. So this is an abstraction. Certain kinds of details are left out. But I'll get to sort of real code analysis towards the end. Okay, so for people who know Puppet, for example, execs don't work here. I'll get to execs in a moment, how they sort of fit into the story. Okay. All right, any further questions here? All right, cool. So those are files. Another really important resource is packages, right? So what packages? So for example, when you say package ensure present, what your system does is it uses the package manager to sort of create scores of files on your file system. So what we do is we have like a little sort of web service that in containers runs either repo query or apt file. The idea being that you can sort of plug in more containers for more environments, and we get like the list of files that the package creates, and we model it as it's a really long program that sort of creates one file for each file that's returned in the listing. For the purpose of checking determinism, the actual contents of the file is not so important. What really matters is just knowing that each file has a potentially unique content. There's a lot of, the abstraction is sort of complicated, and there's certain kinds of like crazy situations where you can get false positives. For example, if a package creates a file with say some contents X, and then the user overwrites that file with the same contents X, we wouldn't detect that. But apart from those kinds of details, it's an abstraction that works reasonably well. As far as, and again, as far as sort of soundness goes, this doesn't support post-install scripts, if you know what those are. I'll again talk about those kinds of things towards the end. Yeah?
So who's going to manage the real interpretation of the Puppet language? Say the Puppet language is just a declaration of the state. And then
Yeah.
who's going to translate into apt file?
I mean, we do that. So we have a system that...
So it's done by the Puppet package author.
No, I mean, so this is what the Puppet package author would have written. Our system reads in, schleps in all the Puppet code, and for packages, this is what it does to build an abstraction of what the package does, right? So packages fundamentally create a whole bunch of files and directories, and we use, repo query or apt file to sort of get that listing. That's basically all there is to it. Right? Okay, so. Okay, so popping back out a little bit. Oh, and so we've done this for like, I want to say 25 or so common Puppet resource types. There's a bunch of like other crazier ones that are, well, there's a bunch of sort of Mac OS and Windows specific Puppet resources that we haven't dealt with. We've sort of focused on Linux, which is the more common use case. Okay, so popping back up a little bit. You can think of the semantics of one of these programs as so when I say these programs, I mean these programs that we're generating from Puppet manifests. You can think of these as functions that sort of consume a file system and produce a file system. So you get an input file system and we produce a file system, unless of course preconditions aren't met, in which case an error is signaled. So that's what the type there is. But when you put these programs together in a resource graph that isn't sort of fully constrained, the programs may run in any order, and so the semantics becomes, we get an input file system and we produce potentially a set of file systems including errors. All right? So now what you can do is, so the property of determinism is simply ensuring that for all input file systems, the cardinality of that set is 1. Right? Each input file system should produce exactly one state, and that state may be error, but that's okay. So given that, what we do is, so you can take a function with that signature and think of it instead as a relation between a file system and a file system. And then you can sort of specify non-determinism relationally like this, right? So think of non-determinism as, well, basically, if you can show that there exists 3 states, sigma 1, 2, and 3, such that they're related like this, where sigma 2 and sigma 3 are not equal, what that means is on this input state, sigma 1, we get to 2 different input states, sigma 2 and sigma 3. So that's what it means for a manifest to be non-deterministic, right? Okay, and so what we're going to do, and I'm not going to get into this in detail, is given this sort of relational specification, we then model the semantics of our language in a SAT solver in the Z3 theorem prover, and use the theorem prover to sort of either find sigma 1, sigma 2, and sigma 3, which then shows that the manifest is non-deterministic, or if it can't find one, that tells us, I mean, that's essentially a proof that it is deterministic given our model. Okay, so there's a couple of issues in pulling this off. So I think we're talking about 3 of them. Yeah, so first, this only works. So this whole encoding this problem as a SAT solving problem only works well if you're reasoning about a finite set of states. And if you think about the space of possible file systems, that's essentially an infinite space. The other problem is that the size of each state is exponential because we're dealing, each state represents a file system. And the other is that if you do this naively, translating that graph into a formula that encodes all possible interactions produces a formula that's exponentially large. So this is all great, but we're not off the hook yet. Just for people who know things about SAT solvers, we're talking about formulas on the order of, we're talking about formulas that have on the order of 1 billion variables, which is intractable for even contemporary SAT solvers. Okay, so how do we deal with this problem? So the first thing we're going to do is we're going to use an old technique called partial order reduction. It's a really simple idea. Basically, if you have a state and you have 2 sort of actions that you're applying, the sort of square action and the circle action, and you can prove that they commute, well, you don't need to explore both paths. You can just sort of explore that one or the other one. All right. So the way you normally do this kind of check is by having some sort of so what this means is that you can generate that graph instead of this graph, assuming that you can do this and do this fast. Now, the way that this normally works is that you look at these actions or these programs, square and circle, you sort of calculate the set of locations that they read and write. And if you can show that you have 2 programs that don't write to the same location, which is what these overlapping sets show, then it doesn't matter in what order you sort of run them. Okay, so I mean, this is the kind of thing that becomes relevant when you're doing like analysis of like concurrency programs and whatnot. Okay, so that's fine. Unfortunately, this doesn't quite work in the context of Puppet mostly because of packages. So the semantics of a package is that it creates its directory tree if necessary. So what that means is that a package, two packages almost always may interfere with each other because, we have a set of common files, standard system paths in which programs are installed, and 2 packages may need to sort of create that directory tree if necessary. And like /opt is a great example because that's a pretty common path but doesn't always exist in base systems. Okay, so what's needed is a sort of commutativity check that's specialized for this domain. And what we essentially do is something like this. We basically abstract programs not just to the sets of locations that they read and write, but we also sort of abstract them to the set of directory trees that they create. Right? And once you do that, you can actually do the sort of fast check. You can sort of take two programs, see that they definitely don't interact with each other in any way, and just sort of consider one ordering instead of both orderings. And once you have a common thing to do is to have like a manifest that installs, I don't know, let's say 10 packages, and you know that you don't have something crazy like that Perl Go example that I showed you earlier. Let's say you have 10 packages and no conflicts between them. And you can rely on the system package manager to sort of install them in the right order and sort of install dependencies as necessary. So there's just no need to specify dependencies in between them. And if you sort of do the naive thing, the usual thing, you'll sort of run into this problem, and the system would have to sort of consider all possible interleavings of these 10 packages, which is, 2 to the 10. On the other hand, if you use our sort of specialized commutativity check, it's able to figure out that packages sort of don't interfere with each other. Yeah?
Do you get any weird cases where the make-dos set some property of the directories, like permissions? Yeah,
okay, so in this in this work, we didn't model permissions. It turns out that when you're talking about that's not something that typically happens. That's typically not the cause of determinism bugs. Makers do set permissions. There's something I want to talk about briefly towards the end where we get into modeling permissions in great detail, because permissions turn out to be relevant for this other problem I'm going to talk about. The thing to keep in mind, in a couple of slides, I'm going to show you like benchmarks. Thing to keep in mind is that those benchmarks assume that models don't have permissions in them. So once you have permissions, things become a little bit slower. Okay. Any other questions? All right. So that's one thing. So that sort of deals with the problem of formulas that are exponentially large, right? So once we're able to sort of take, instead of generating this, I mean, the trick is one way to do this is to generate this thing and then prune it down to that. That doesn't help because you still create the exponentially large objects. So the trick is to leverage this check to directly generate that and never generate this. Right? So that deals with the problem of formulas being exponentially large. So I want to briefly talk about the problem of state size. Okay. So so the main thing that we're modeling is the state of files in the file system. Really the state of paths in the file system, to be precise. So a path there may be nothing at that path. The path may be a directory. The path may be a file, and so on. And so, for example, let's say that you have a simple package that installs Git, because Git and the LXD icon theme package, to pick a random example, which installs like 7,000 icons, right? Because it has to, right? So if you think about how we model this, right, we take these. So this will turn into, using our sort of crazy Docker-based, apt repo query toolchain, this will turn into a program that essentially creates 500 files. That will turn into another program that creates 7,000 files. The way you model this is that you say, all right, in the initial state, I have 7,500 files that don't exist. Then maybe I run Git, and that creates 500 files, and 7,000 files don't exist. And then once I install that package, all these files exist. So that's why states are really large. Okay, because we're sort of tracking this. If you do this naively, we're tracking the state of all of these files. But I mean, come on, think about it, right? Like Git and this package of icons are not like interacting with each other in any sort of interesting way, right? So this is like a dumb problem to have. So let's think about the property that we're actually interested in proving, right? So we don't actually care about modeling Puppet in all this gory detail. All that we really care about is proving that things are deterministic, or sort of coming up with a counterexample that shows that two resources in different orders produces something that's non-deterministic. So again, thinking back to commutativity, if you can sort of identify like a block of code in, let's say in my square, so let's say this blue triangle, and you can prove that it sort of commutes with everything else in there, you can actually, it turns out that inequality holds, even only if that inequality holds because of commutativity, and then you can actually pull blue out of the equation completely, and that inequality holds, right? So basically, what we're able to do is build up this big model, and then sort of pull out chunks that don't matter. So let me show you at a high level what that means. So let's say you have a manifest that looks like this, and this is actually this is like a common bug in at least from what we've seen. So we're installing the Apache package, and we're creating an Apache configuration. But out here, what happened is that the user forgot to say that, oh, we should only create this file after the package has been installed. Okay, so what our system will do is it'll take all the hundreds of files that Apache creates, and it'll say none of these files matter for the property that I'm trying to prove, which is non-determinism, but it will keep around the Apache 2 file because it does interact with this other resource. Okay, or here's another example. Let's say that we're creating two user accounts, Arjun and Ryan, and I'm also creating a file in my home directory. If this is all that you're working with, our system will sort of prune out everything that has to do with the Ryan resource, but keep around /home/Arjun because it interacts with that file, right? And so these are some of the tricks that we use to, shrink down the sort of space of the state space. Yeah?
When you say you prune files that don't interact with anything else, do you just mean that, like, so if Apache writes a file like user bin Apache,
Yeah.
anything else like reads or writes that file and can be pruned? Like, what's the property that makes it?
So it's about whether let's say you install Apache and it creates user bin Apache, and then you have some other resource that reads or writes to it. Then that path can't be proved because it may be, that there's some sort of non-deterministic interaction with it. But in practice, like, I mean, if you're doing something else with user bin Apache, you probably aren't doing anything else with user bin Apache, right? So in practice, those kinds of paths will get pruned out from the model, right? So this is just so basically we create this super detailed model to account for sort of everything that could possibly go wrong, and then these tricks help sort of prune out the things that sort of obviously don't interact in ways that are non-deterministic.
So this is sort of asking the question again, but is the property for not being pruned that there exists a pair of resources that touch a path, that like read and write, that both write to that path or something, or both write? Yeah, well, what is precisely the prune?
So the precise property is sort of this. So let me try to explain it. Let me try to explain it in more detail, right? So imagine that square and circle are boxes that represent the program that abstracts of two different resources, right? And what we're trying to do is show that, to show determinism, what we're trying to do is show that when you run them, square followed by circle, you get a different result than when you do circle followed by square, right? And so we're trying to sort of find some input state, sigma, that will drive these two programs to produce these two different orderings of the two resources to produce a different output. So the property, the property is that if you can sort of find like a section of code in Square that you can sort of commute with everything else, then that inequality holds, if and only if that inequality holds.
So you're doing this
yeah,
pairwise analysis.
Yeah.
You'll do this analysis of whether individual pieces can be pruned. It's not like globally you prune things. It's like as you're doing individual.
Right. I mean, so what we're actually doing is that so let me back up a little bit more. So we are generating formulas that represent graphs that look like this, and what we're actually trying to do is we're trying to take like fragments of resources and moving them down to the leaves where they're like the last thing that's done. So if you can take a chunk of code and push it down to the very leaf of this formula that we're generating, what you're effectively saying is that, this is the last chunk of code that I run, and whether the program is, and whether these two paths lead to different results or not will not depend on whether this chunk of code runs. And so then you can pull out the chunk of code, and so long as if the chunk of code is working with a set of paths that nothing else uses, well, then you don't need to reason about those paths at all. Right, so there's a chunk of code that creates, let's say creates user bin Apache and a bunch of those other things. If you can sort of push it all the way to the end on all possible paths and nothing else works with user bin Apache, well, then you don't need to represent user bin Apache at all in the model. Is that a bit clear? Okay. All right, so where was I? Okay, cool. So one last technical detail I want to talk about is about finite stateness. So all this term-proving technology and whatnot is, I mean, it works well if you're dealing with a finite state space. So the problem, of course, is that file systems are effectively potentially infinite. There's effectively an infinite space of possible file systems that you may need to reason about. And so here's something that you may observe. So if you take a Puppet manifest, it's only like creating a fixed set of files, right? So like maybe you're dealing with a few hundred thousand files. So it seems like all we need to do is reason about the files that are like mentioned in the manifest. So we don't need to actually consider, for example, some other random path. Like if all we're doing is installing Apache, we don't need to think about the paths that the Nginx web server creates, right? We can sort of work one manifest at a time. Okay, so this is almost true. The only caveat has to do with how empty directories work. So so let's say you have this program P here, which checks to see if /A is a file. If so, it removes it and then creates /A. And this other program, it simply creates /A without trying to check if it's a file. These programs aren't equivalent, right? So there is a file system state which sort of shows that they're different. And what that file system's and to reason about that, and you don't need to think about all possible file system states. You just need to sort of, think about file systems that have the path /A. But consider these two programs, right? So what this program does is it checks to see if /A is a directory, and if so, it does nothing, and if not, it blows up if it's not a directory. Whereas this other program, Q prime, it checks to see if /A is an empty directory, and in which case it sort of does nothing, otherwise it blows up. So these two programs are different, but to reason about the fact that they're different, you need to sort of say, well, imagine there was a path, imagine there was a file inside /A. Right, so it's not enough to just look at the paths that are mentioned in the program to distinguish these, to tell that these two programs are different. You need to say, well, you need to also sort of add another path to your to the set of paths that you're reasoning about to tell those two programs apart. Okay, so there's some subtlety here. If you do the naive thing, you'll get a result that's unsound. Once you sort of realize that this is sort of a test that programs do, you sort of have to add a few more points to your representation of state, and it sort of works out. Okay, so in the time that I have, okay, so let me do this. I think I'm going to hazard a very quick demo of what our system does before getting onto like numbers and whatnot. And I'm off the Wi-Fi. I blast. This will hopefully get me back on without much drama. Well, and it's not going to ask me for like. Let me go to like a website. Let's go to Yahoo. I haven't been there in a while, and so I should hit that. Okay, good. I don't want to get to something that's cached. All right. Okay. So here's a little like web-based demo of what our tool does. So there's a couple of like sizable examples here, and we'll talk about them once I show you some benchmark results. So let me just go over a really simple one. So here's a really simple. Can people read this, by the way? Okay, let me make it a little larger. Well, this is Bootstrap being super clever. Is that a little better? So this is just the example that I had earlier. I have creating a package Vim, the file home Carol vimrc, and the user Carol. And so when you run our tool, it's called Rehearsal. It sort of, thinks for a little while, and it comes back with this. It says, checking if manifest deterministic failed. And then one thing that's nice about the system is that it reports the failures as a fragment of Puppet code. So it says this dependency may be missing. And so in this example, you can actually copy this fragment of code, paste it in here, run it again, and comes back and saying it's deterministic and it's idempotent. I'll get to idempotence in a second. It's not always safe to do this. It's not, you got to read error messages and process them and make sure that they actually make sense. So there's some examples here where there's some examples of manifests where it comes up with a correction that will make it deterministic, but if you're honest with ourselves, it's not the right fix. Anyway, that's sort of linked to from my website. So let's go back here. Yeah?
So is part of the way this is running, is this literally like spinning up a Docker instance to like run the little snippets to generate their interpretations, or is that like done somehow in advance so you know
the interpretation, to generate the interpretation, I mean, we have our own, the interpretation of each resource is sort of we've written it ourselves in our modeling language. So Docker is not necessary there. The Docker instance is necessary to come up with an interpretation of packages. So to come up with an interpretation of package, we need to sort of run repo query or apt file to get the package list. It's not doing that live in this case. I mean, it has a little cache. But if you throw in some package name that, I haven't tried, it'll spin up a little Docker instance and do what it needs to do. Okay, so that works, amazing. So let me skip through that. back up slides. Okay, so quick graphs. All that's sort of happening here is that I'm sort of pointing out that all the sort of hacks that sort of reduce the size of the state space are really necessary. So here are two manifests that are sort of timing out if you don't have all the hacks and you just sort of model the thing naively. But with the optimizations and heuristics, the manifests are sort of analyzed in a second and a half or so. There's about, I think 13 or 14 benchmarks on this graph. And a couple of them are marked non-det, which means they were non-deterministic. So these are all, to be clear, these are all like manifests that we found by like scraping GitHub. And so there are a couple of manifests that we found that were truly non-deterministic. And as far as what's happening here, the reason that with our heuristics things go a lot faster is because what our heuristics do is they sort of cut down the number of files that the system needs to reason about. So without a heuristic here, for example, this one, which times out, has a model that's sort of reasoning about 1,500 files, and 1,500 files plus all the possible interleavings of resources makes the thing time out. But with our heuristics, it cuts the number down to like 250 files or so, right? So it's sort of pruning down the model to just a set of things that may interfere with each other and don't obviously, and it's sort of leaving out the things that obviously that don't obviously not interfere with each other. Okay, so yeah.
I had a question about how you model the file system abstraction.
Yeah.
Started going into this detail when you had to worry about whether the directory was empty or not.
Right.
Is that kind of like a detail of the abstraction that you kind of left out to add? Is that sort of an example of that layer of the abstraction? Like, did you also have to worry about, for instance, like sort of like a hash MD5 sum of like the files after they're installed, or did you worry about?
Yeah. So for this work, we model sort of file equality. So the system reasons about whether files are the same or not. It doesn't model like contents in any detail. So if you have a manifest that like reads the content of a file, like cuts it up or something, and puts like half of it here and half of it there, that won't be captured accurately. On the other hand, if you have a manifest that's sort of copying one file from here to there, that will be modeled precisely. So we model, we also model directories and empty directories in great detail. Something else, as was asked earlier, something else that we don't model are file permissions and modes and things of that sort, because they don't seem to play a role in these kinds of determinism bugs in our experience. But there's something that I'm going to talk about very briefly towards the end, where we sort of bring that back in. Right? Okay, so so the upshot of all this, so once you do all this, you prove that the darn manifest is dealing with is deterministic. What you really get is this. So you get to go from this sort of relational semantics for Puppet to thinking of Puppet programs as just functions from input file systems to output file systems. That's really what determinism gives you. Okay, and once you know they're dealing with functions, a whole bunch of other things can be done. So for example, we looked at this briefly in the demo, sort of proving that a function is idempotent is super easy with like a stat solver, f compose f equals f. The other thing you can do is sort of check preconditions and postconditions. That's something else that the web-based demo shows. If you have this little goofy assertion language, which lets you write down postconditions if you want. There's certain cases where I can imagine that being useful. What I like about determinism and idempotence is that they're sort of like these meta properties that you sort of always want, and you don't have to like come up with annotations or anything of that sort. So what's this? Okay, so this is another graph that sort of shows that checking idempotence is fast. And the reason that this is fast is not because we did anything clever. It's because we're just dealing with functions. Yeah, it's really fast. Okay, so in another minute or two, I want to briefly talk about sort of two other things that we're doing in this space. And this is a little more work in progress. There's not like, published graphs yet. Something that I've alluded to earlier, something that we're ignoring in Puppet so far is shell scripts. So I've shown you that Puppet has all these, beautiful abstractions for creating packages, files, and all of this stuff. And the point of this is that you should be using these abstractions instead of writing your own shell scripts. Unfortunately, there are times when you really have to do that. Okay, and this is my favorite example. So let's say that you wanted to install the Oracle JDK on a Linux machine, right? We all want to do this because OpenJDK is terrible. Okay, so this is what you have to do. So it's like not standard on Ubuntu, at least the last time I checked. So you got to like add a PPA, update, and run Oracle Java 7 installer, right? So have people done this? I'm just curious. Okay, a couple of people were programming in Scala, presumably. Okay, so so it's easy to take this and translate it into a Puppet manifest that looks like that. Unfortunately, when you do that, it doesn't work. It sort of blows up in your face. Does anyone know why? Yeah. Yeah. So Oracle, in their infinite wisdom, has one of these interactive license screens. And since Puppet runs in a non-interactive shell, it sort of says, well, I can't show you the license, so I guess you didn't accept it, so fail to install package. Right, so how do you solve this problem, right? Okay, what you do is you go on a Stack Overflow and you ask, how do you say auto yes to, the license agreement? And then the answer with the green check mark sort of has that little script. Doesn't matter what it says, you just sort of blindly paste it into your manifest using the exec resource type, which is just short for resource, which is just like a shell script, and it works. Right? So I love taking shell scripts from the internet and sort of running them on my console. Okay, so something that we've been working on currently is learning finite state models of shell scripts from IO examples, sort of running them in containers, perturbing the input, looking at the S trace, trying to sort of drive it to explore different states to learn a finite state model. So I want to emphasize that a really hard problem would be if I told you, here's wget, come up with a model of it. Like, that would be a really hard problem to solve. But that's actually not the problem that we need to solve here. The problem we need to solve is more like model wget that URL. So it's a much simpler problem to work with. We're not trying to model like commands given arbitrary input. With the way you use shell scripts in a Puppet manifest is that you're invoking it with particular arguments. Okay, so the other thing that we're working on is a little bit different. So the point of doing this is that once we do this, we'll be able to send many more manifests through our system. I think we found that at least about half the Puppet manifests that are out there on GitHub use embedded shell scripts, and our tool won't work until we get this thing working. So the last thing I want to talk about is a slightly different problem. So and it has to do with sort of fixing bugs. Okay, so let's say that you write this manifest. It's creating a vimrc file that says column number mode true, right? You deploy it on a machine, and then you look at it. You got a test. It's easy to show that it's deterministic. You just look at a test. So you test by firing up vim, and it says error detected while processing. So that's how you turn on column numbering in Emacs, right? So how do you fix this problem, right? So you remove the file, so that you make the error go away. You fire up vim, let's say, and then you type in set ruler, because that's how you turn on column numbers in vim. And then you fire up vim again, you observe that everything's okay. And well, unfortunately, what you need to do is you need to then sort of apply this edit back to the manifest and test again just to make sure you didn't make a mistake the second time. So something else that we're working on now is, so basically what you need to do is, original configuration followed by a bunch of shell commands, but then you need to sort of come up with the updated configuration. So what we're working on is effectively calculating this configuration update given the original configuration and the sequence of shell commands. It's sort of a search problem in a funny domain. Right? And I think that this will sort of, one way to think of it is that Puppet development has like a really, really long sort of edit, compile, debug loop. You got to deploy a system, and this will hopefully make that loop go a lot faster in certain cases. And there's a bunch of sort of interesting problems because it's often the case that there may be several possible configuration updates, and that's something and that's really what we're sort of exploring right now is how do you present several possible updates to the user. All right, so that's all I wanted to talk about today. Thank you all for coming. I'm around and I'll be happy to take any more questions if you have any.